Now, why we need to study this? So, this Heisenberg uncertainty principle is having some applications. Among them, according to your syllabus, there is one application which is kept, that is non-existence of electron inside the nucleus of an atom. As we already know, electrons can reside only outside the nucleus. Inside the nucleus only proton and neutrons will come. They will be there. Then what is the question of rising the existence of electron or non-existence of electron inside the nucleus? The question comes. So, as you already studied one more topic, that is radioactivity phenomena. In that radioactivity phenomena, you know that the alpha particle, that is helium nucleus, or beta particle, that is an electron, again in beta, beta plus and beta minus will be there, that is electron and the antiparticle of an electron, they emit from the nucleus, right. So, if you take a uranium radioactive element or plutonium radioactive element, those elements will keep on emit the radiation and they change themselves. So, when it emits alpha particle, its atomic number changes by 2, reduces by 2, and its atomic mass changes by 4, because alpha particle is a helium nucleus. Similarly, when it emits a beta particle, that is an electron, okay, which comes from the nucleus, if the electron beta minus, that is electron, if it emits, then there is an increase in its atomic number by 1 without changing in its atomic mass. Okay, so then the question comes, is this electron, that is a beta particle, coming out from the nucleus? So, experimentally we know that yes, it is coming from the nucleus, and the energy associated with that particle, if we measure, it is around 3 to 4 mega electron volt. The energy associated with the beta particle is 4 mega electron volt, is the maximum energy. Then definitely the question comes that the electron exists inside the nucleus or not. So, for that, electron never exists inside the nucleus. To prove that one, Heisenberg uncertainty principle is one kind. So, here what we do is, we will consider two cases. One is the case of this, that is energy is connected with the momentum, that is E is equal to p square by 2m. If I differentiate this, you will get this equation, that is delta P equal to delta E by V. So, here we will consider a nucleus, okay. So, nucleus we will consider. So, we will consider a nucleus of an atom. As you know, the periodic table, from the first element, that is hydrogen, till the radioactive elements, if you consider all of them, the highest diameter of the nucleus we need to consider as the uncertainty in its existence. That means, if the electron exists inside this nucleus, then it should be within this diameter, because we are considering nucleus as a spherical in shape. So, the electron should exist within this diameter. Let us say that diameter is of about 10 to the power of minus 14 meters. So, that means the uncertainty in its position to exist, that is the maximum uncertainty it is, because we took the bigger sized nuclei. So, for that delta x should be maximum, which we considered as 10 to the power of minus 14 meters. Okay, so 10 to the power of minus 14 meters is the uncertainty in its position. If this is the case, then if we substitute this value in the momentum, as the product of uncertainty in its momentum and position is constant, that is h by 4 pi, where h is a Planck's constant, which I already told it is 6.626 into 10 to the power of minus 34 joule second, which is constant, and pi is also constant, 4 is also constant. Then the product of these two, when you consider, if delta x is maximum, then definitely the delta p should be minimum. So, if we evaluate this delta p value, then it comes out as h by 4 pi into delta x maximum. Now, h value is known, and then we know the delta x value as 10 to the power of minus 14, pi is 3.14 to substitute. then we will get delta P minimum as 5.8 into 10 to the power of minus 21 kg meter per second. So, in this order you will get it. So, this is delta P minimum. Now, if I substitute this delta P minimum itself as the momentum required, then you can calculate the kinetic energy associated with this as P square by 2m. So, if you substitute this value and if you simplify and if you express this kinetic energy in terms of electron volt, then it comes out as around 95 mega electron volt. M is capital here, mega means 10 to the power of 6 electron volt, order of 10 to the power of 6. So, it is around 95 mega electron volts. But we saw in beta particle, the highest energy with the particle is 4 mega electron volt. Here, the minimum energy which is required is 95 mega electron volt if the momentum possessed by the particle is this much. Hence, we can consider there is no existence of electron inside the nucleus. But there may be another chance, like the electron exists, but that electron is not stationary, that electron is moving very fast within the nucleus, say it is nearly equal to the velocity of light. Since the electron is moving nearly equal to the velocity of light, because of that we are not able to tracing the electron, but it comes out as a beta particle. If this question comes, then for that also we have to answer. So, for that we must consider the theory of relativity, where the energy mass relation, you can express it like this. Here this mass m naught is called rest mass of the electron, which is 9.1 into 10 to the power of minus 31 kg, whereas m is the mass which is depending upon the velocity of the particle, how much it is. V is the velocity of the particle and c is the velocity of light. So, you know the Einstein's mass energy relation, E is equal to mc square, well known equation. In this, in the place of m, we will consider m naught by under root 1 minus v square by c square. This relation is from theory of special theory of relativity. So, with this equation, if I square it, you will get this equation. Just to remove the square root, you can square this equation, then E square equal to, you get this equation, call this as equation number 1. Next, same way, from the definition of momentum, P is equal to m into V. Again here, put the value of m in relativistic form, that is m naught v by under root 1 minus v square by c square it comes. Here also to cancel the square root, square it, then you get this equation. So, call this as equation number 2. Now, what we will do? We will match the dimensions of these two equations by multiplying c square. P square is multiplied with c square, so that the dimensions of this equation 2 is same as the dimension of equation 1. Then this is a square of energy, this will also be a square of energy. You can take their difference, that will be the kinetic energy which is required. So, in that way, when you take this equation, that is E square is this and P square C square is this. In this, you can see C square minus V square is the LCM, common it is. Then in the numerator you will have m naught square c to the power of 4, and again you can take c square minus v square as a common factor from these two equations. Here v square is there, here c to the power of 6, in that c square you can take it as a common factor. You left with c to the power of 4 here and you left with c to the power of 4 here. So, m naught square c to the power of 4, if you take it as a common factor, then you left with this. So, these two are same, so it get cancelled, then you will get the equation of this kind. So, or you can write E is equal to under root of P square C square plus m naught square c to the power of 4, which is one of the famous relativistic case of relation which connects energy with momentum and rest mass of the electron. So, now if we consider that and if you calculate the E value, then you can see the energy possessed by this in the relativistic case, it comes out as 9.4 mega electron volt. So, here it should be capital V. Okay. So, 9.4 mega electron volt. Always when you write electron volt, small e, capital V you should write. and here mega, capital M, mega, small m if you write, it becomes milli. So, mega electron volt. So, in this way, both in the non-relativistic case, that is 95 MeV, and in the relativistic case, it is around 9.4 mega electron volt. These are the minimum energy expected for the electron to exist inside the nucleus. But according to the experiment, maximum energy possessed by the electron which comes from the nucleus, that is beta particle, is about 4 MeV. So, there is no comparison of these energies. Hence, we can conclude here that presently whatever the assumption or the hypothesis which we made, that if the electron exists inside the nucleus, then it should be within the diameter of the nucleus, that is considered as wrong. Or in another way, the hypothesis what we considered in the beginning is a negative hypothesis. Like this, using Heisenbergs uncertainty principle, you can prove the non-existence of electron inside the nucleus. But how the beta particles come from the nucleus? For that, later on, you cause meson exchange theory, which explains the non-existence of electron inside the, existence of electron inside the nucleus. That it will be studied in higher studies. That is specifically for physics stream, those who are in master's degree, they will study. So, for you, using Heisenbergs uncertainty principle, how to prove the non-existence of electron inside of the nucleus is sufficient. So, like this, there are so many applications associated with the Heisenbergs uncertainty principle. Okay, like Bohr's atomic theory also, you can explain why the electrons which are revolving around the nucleus in the Bohr's atomic theory, why these charged particles when they move, they don't emit radiation. Because as you know, any particle, charged particle moving, it should emit radiation. But in that case, it won't happen because of, again, the wave pattern of the electron. So, like this, there are so many applications associated with this. So, this is what one of the important topic in module 1. Okay? Thank you.